Okay, so let's talk about the next section. We're talking about rational equations, which we just did in the last one, and actually solving problems. In other words, storytelling. Here are our objectives. We're going to solve equations containing those rational expressions for a specific variable. And then we're going to solve number problems by writing equations containing rational expressions. We're going to have to write the equations, but we can do it. We're going to solve problems that are modeled by a proportion. We're going to solve problems about work, and then distance, rate, and time problems. All right, so we've got 5 different types of problems we're going to work on. So here's our first example. We are going to solve this problem for a specific variable, right? So notice I have an equation with a bunch of fractions in it, right? Okay, so what's the very first thing we need to do? Correct. Find the LCD. That's what we need to do first. Find the LCD. And I'm hoping that you all realize the LCD would simply be taking the 3 denominators and multiplying them by each other. Do you agree? Good. Now, after we do that, remember, we need all these denominators to look like the common denominator. So denominator number 1 has an A, but it also needs to be an X, don't it? Or I should say, doesn't it? So top and bottom. Denominator 2 has the B, so it just needs the A and the X. And denominator 3 has the X, so it just needs the A and the B. Okay? And when we do this, we end up with the equation that looks like bx over abx plus ax over abx equaling ab over abx. Okay, so after we make all the denominators look the same, what do we do? That's right, we clear the denominator, we clear the fractions. So remember how we do that? Yes, we multiply everything by the LCD, which means in this case, all 3 of these fractions will get multiplied by ABX over 1, because we have to make a fraction, or we should multiply a fraction by a fraction. So then ABX's top and bottom all cancel out, don't they? Which means what remain is simply BX plus AX equals AB. So just like we did in the last section, yes? This is nothing new, is it? Okay, but now we have to stay focused. We are so used to solving for X that we forget there are other variables now. There's, in this case, an A, a B, and an X. Which one do I solve for? Go back to the top. They want us to solve for A. I need to isolate A. I need to get A on one side so I can solve for it. Okay, so A is on both sides, isn't it? So which side do you want to bring the A's to, the left or the right? I'm hoping you said the right, because the right side already has an A, and so it would be best to bring this A, X, to the other side. And the way we do that is by simply, subtracting. So it's going to look like BX equaling AB, which was already over there, minus AX. And again, if you're very visual, please make certain that you put these little notes under your work so you can see what's going on. Okay, good. So, got that taken care of, yes? Love it. Now, all my A's are on one side, but do you notice the A is written twice? A needs to be written one time. And you actually know how to do this. Remember, this AB minus AX looks like it was almost a distribution problem, like A got distributed to something. So if this looks like a distribution, then we have to go backwards And backwards of distribution is, yeah, factor. Factor goes backwards. So we have your bx equaling. And if I factor out what's in common, I can factor out the a. And now a is written one time, isn't it? Cool. Which means last but not least, I need to finally solve for a. And when I do that, I'm going to divide both sides by that parenthesis. And a is by itself. And again, if you need to, make certain you put your work under both sides so you can see what it looks like. Okay, you know if you need to write these little steps in. Yes? Cool. Okay, now I need to elaborate on something. On step number 4 here, we don't always have to factor. Okay, this case, we needed to factor. All right, but that's not always the case. A does need to be written one time, but sometimes I don't have to factor to do it. Sometimes it's already written once. Good? Okay, loving it. Let's look at the second example. The second example is I need to translate this problem. It says the quotient of a number and 9 times its reciprocal is 1. They want us to find the number. Okay, there are certain key words in this problem that tell me what to do. Gratefully, there's no fluff. So, do you remember what the word quotient means? Yeah, that means to divide. Do you remember what the word reciprocal means? Yeah, that means to flip over, right? Do you remember what is means? Yeah, that means equals, right? Remember what the word times means? Yeah, that's multiplication, right? So there's key words here that tell me what I need to do. So, step 1, let's understand the problem. They said the quotient of a number. Do I know the number? No. So we're calling the number a. And then it said 9 times its reciprocal. English language is interesting. It uses it, they, them to represent something you just spoke about. Well, if I'm looking at a quotient of a number and its reciprocal, the it refers to the number. So I'm looking at the reciprocal of this number, 1 over n. Does that make sense? Remember, reciprocal means flip it over. If my number is n, I flip n over, and by the way, you can write n as n over 1, can't you? And when you flip it over, then you get the 1 over n. Yes? Okay, let's take a closer look. We have the quotient, which we already discussed was division, of a number. There's our n. And 9 times, remember what times means? It means multiplication. So there's the 9, and there's a little times in between here. The reciprocal of the number is meant equal, and then we have 1. Agreed? And this is what it looks like. Okay, so remember what we worked with first. Yeah, we work with parentheses first, don't we? So we have to simplify this first. We have to simplify what's in the parentheses first. And when you simplify it, it's just 9 over n, isn't it? Okay, so how do you divide fractions? Yeah, you multiply, don't you? We never divide fractions. We end up multiplying by the reciprocal, don't we? Okay, so if you write this, I'm going to back it up a second. There's a middle line that I am going to put right here. And my middle line would look like n over 1 times n over 9 equaling 1. Yes? And then I would have n squared over 9 equaling 1, wouldn't I? Okay, I have a fraction. You want to keep it? Correct. We don't. So we're going to multiply both sides by that denominator so it cancels, which leads me into this line here, where n to the second would equal 1 times 9, or just 9. And to solve, you need to take the square root of both sides. Remember that. Remember also, the square means I'm supposed to get 2 answers. I know the square root of 9 is 3, but some people forget that negative 3 is also the square root of 9. Because doesn't negative 3 times negative 3 equal a positive 9 also? Yeah. Cool? Okay, but we got to check our work. We have to make sure that our answers work. And notice something. Back to the original problem. It said the quotient of a number and 9 times its reciprocal is 1. Find the number. Did they say anything? Did they say anything about this number being positive or negative? No. Which means it can be both. So if we go back to our interpret, we are going to check. Here is plugging in the positive 3. Here is plugging in the negative 3. And when you do the work, we end up with both statements being true, which means both positive 3 and negative 3 will work for us. Cool? Okay, so let's go on to another example. Ratio. Here's another word for ratio, fraction. Whenever you see the word ratio, if you think of fraction, you're good to go, okay? So in other words, A over B, or X over Y, or whatever over whatever, all right? A proportion. Notice what it says. It's a mathematical statement that 2 ratios are equal. Well, we know what equal to means. It means equals, right? And ratio, we just spoke about. Ratio means a what? That's right. Ratio means a fraction, which means I could have something that looks like this. And now I have an equation with fractions in it. And we solve it just like we did in the last section, and just like we did today in this lecture with a couple of other problems. Make the denominators look the same and then get rid of them. Okay, one more, a rate. A rate is also a ratio, and a ratio again is a fraction. But let me give you an example of a rate, because you're like, what the heck is a rate? You deal with rates all the time. If you go buy gas, they say, hey, it's $3 per gallon. That's a rate. $3 per gallon. Or if you drive your car and you're like, okay, this residential area says 25 miles per hour, your speed limit. Well, that's 25 miles per hour. That's also a rate. Or if you are going to buy meat and they say, oh, this package of meat is $5 per pound. Those are all rates. Okay? All right. So let's take a look at how we solve these guys. Now, I want you to see how we get here, because once you understand how to get here, then it's easy to do. Notice something first. I have one fraction equaling one fraction. That is the only time that you can do this cross multiplication. That's the only time. Only one fraction equaling one fraction. So let me rewrite this problem so you can see how it gets there. So I have A over B equals C over D. And remember, we want our denominators to look the same, which means I would multiply the first fraction by D, top and bottom, fraction number 2 by B, top and bottom. And so now I end up with AD over BD equals BC over BD. And remember what we do next. After the denominators are the same, we do what? Yeah, we get rid of the denominators. denominator by multiplying all fractions by that common denominator, so they cancel. And I simply end up with AD equals BC. That allows me to multiply over the equal to sign, A and D, and over the equal to sign again, B and C, which is how they got this AD equals BC from the work here. Good? Again, the key is you can only use this technique when you have one fraction equaling one fraction. That's it. If you have two fractions on the side, forget it. You have to do like we did in our last lecture notes on solving these guys, solving rational expressions. Now let's take a look at this problem. I have a 170-pound person, and they didn't say where this person is, but we have a 170-pound person, weighs approximately 65 pounds on Mars. And they want to know how much does a 9,000-pound satellite weigh. Okay. I'm assuming this person is on Earth. They didn't say it, so I'm assuming that this person on our planet weighs 170 pounds. And on Mars, they weigh 65 pounds, right? And they want to know how much does a 9,000-pound satellite weigh. You know, the English language is quite interesting. They're assuming a lot of things. This 9,000-pound satellite, where is it located? Is it located on Earth? Is it located on Mars? Where is it located? These are some of the things they're assuming that you can figure out based on what they wrote. So, how much does a 9,000-pound satellite weigh? This 9,000-pound satellite is on Earth, which means they want to know how much it weighs on Mars. Got it? Okay. Now, here's the thing. I'm only talking about two items. I'm talking about the weight on Earth and the weight on Mars. I'm only talking about two items. And because I'm talking about only two items, this is perfect for a proportion. Notice how we have it set up here. And I like the way they wrote this because this is very important. On this side, they put the Earth weight. On this side, they put the Mars weight. And they purposely put all this writing here so you realize this is the same on this fraction. In this fraction, we're talking about the same thing. And on the other fraction, they did the same thing. On Mars. So we have the same thing we're talking about over there. Now, let me back that up a second. And let me do just a little bit of a rewrite. Because in math, we usually don't write the words. So basically, we have 170 over 9,000 equaling 65 over x when you take the words out. Do you agree? Okay. Now, do I have one fraction equaling another fraction? Yes. Because I have one fraction equaling one fraction, I can use this cross multiplication that we talked about in the previous slide. I can use this, which means I would take the 170 and go across the equal to sign and multiply by x. And then I would take the 9,000 and go across the equal to sign and multiply it by the 65, which gave them this 585,000. Okay. So that means we have 170x equals 585,000. Divide both sides by 170, and we end up with approximately 341 pounds. Where Wait. What does X represent again? See, here we go. What does X represent again? X is the number of pounds the satellite weighs on Mars. X is the number of pounds the satellite weighs where? That's right, on Mars. Cool? With me? I have only two items that we were talking about. The weight on Earth, the weight on Mars. That's perfect for a proportion. All right. Let's look at another example. To estimate the number of people in Jackson, the population of 50,000 who've had a flu shot, they polled 250 people. Of those polled, 26 had a flu shot. So they want to know how many people in the city might expect to have the flu shot. Now here's the deal. It's very challenging to poll 50,000 people. So what they did was they took a small group of people and they polled those people and they asked them, did you have a flu shot? And in this case, out of those 250 people, 26 had the flu shot. So it gives them a guideline to go by. Are you with me? It's a guideline. Here's my sampling. Here's my guideline. Out of 250 people, I know 26 had the flu shot. So if that's the case, how many would have had the flu shot out of the total of 60,000? So check out how they wrote this. I like how they wrote it. My total population over my polled population. And the total number with the flu shot and the number polled who had the flu shot. Again, I'm talking about two items. The population and those that had a flu shot. Only two items. It's perfect for proportion. This part right here, where they write it in words, to me, that is the most important part. Write the words down. When you can write the words down like this, it's very easy where you're putting your numbers. Total population is 50,000. They polled 250 people. I don't know how many had the flu shot out of this 50,000, but what I do know is 26 people had the flu shot out of the 250. Got it? Okay. One fraction equaling another, yes? So since I have one fraction equaling another, I can go across the equal to sign and I can cross multiply, can't I? And there it is. The 250x equals the 50,000 times 26. Multiplying those two numbers out on the right. And now I can simply solve for x by dividing, can't I? Which tells me x is 5,200. Okay. Remember what x stood for in the previous slide. X was the number of people out of the total population who had the flu shot. So, out of 50,000 people, 5,200 had the flu shot. Are we good? Does that make sense? Okay, perfect. Okay, now, let's look at a different example. I have a roofer. He's putting a new roof on a house. And he can do the job in 26 hours. A beginner needs 39 hours to do the exact same job. They want to know how long is it going to take the two roofers to work together. This is that on the objectives, this is at number 4. This is the work problem because they're working together. Now, I know that the experienced roofer can do the job in 26 hours. I know the beginner takes 39 hours. Do I know how long it takes them working together? No. I'm just going to call it T. Why? T stands for together, doesn't it? Okay, but what I do know is this. If it takes the experience roofer 26 hours, then in a single hour, that experienced roofer does 1/26th of the job. In 2 hours, that experienced roofer does 2/26ths of the job. In 3 hours, that experienced roofer would do 3/26ths of the job. 4 hours, are you getting the hang of it? He'll do 4/26ths of the job. Does that make sense? Getting the hang of it, and so forth and so on. Cool? All right. So now the beginning roofer takes total of 39 hours, which explains why in a single hour he does 1/39th of the job. And they take T hours working together, which I know this sounds funny, but they do 1 over T, 1 out of T of the job in that same hour. Okay, so let me ask you something. If they're working together, what operation is that going to be? Yeah, adding, right? If I add their work, it should equal how much together, right? It should equal how long together. Well, here's the thing. If people are working together, should it take more time or less time to do the job? Technically, it should take less time, right? I mean, unless you're washing a car and you get into a water fight, it should take less time, right? So the fact that this beginning roofer takes 39 hours, when he works with somebody more experienced, it should take less than 39 hours, shouldn't it? Yeah, so for us to add 26 and 39, it's going to be well over 39 hours. So that's not what we're adding together, because it's not the same. What we're adding together is their rate. And this is the rate. How much of the job can they get done in a single hour? Right? They get 1/26th of the job done in a single hour. So it's the rates we're adding together. Not their times, the rates are added together. The experienced roofer, how much of the job he does in 1 hour, plus the beginning roofer, how much he does in an hour, and that should give me how much they get done together in a single hour. Okay, let me back up. So let's talk about this. Time to solve, yes? Okay, so remember, we want a common denominator. And the common denominator between a 36 and a 29, so let's go find it. So I can break down 26 to 2 times 13, can't I? Remember, we factor to find the LCD. 39 is 3 times 13. Whoops. Right? And I want to make them look the same. So denominator number 1 needs a 3, and number 2 needs a 2. Cool? Okay. By the way, we have to remember, we have a third denominator, and that third denominator is a t. Well, t is just t. And that means that this first denominator is also going to need a t, so is the second one. And that t is going to need the 2, the 3, and the 13 both, or all 3 of them. Cool? All right, so let's get back to our original equation. The 26 was multiplied by a 3 and a t, top and bottom then. The 39 was multiplied by a 2 and a t, top and bottom. And the t was multiplied by the 2, the 3, and the 13. Okay, gander what the next line will look like. I'll have 3t over, what's 3 times 26? Yep, hopefully you said 78. And then I'll have 2t over, what's 2 times 39? Hopefully you said 78. And so 2 times 3 times 13, what do you get when you multiply that together? Hopefully you said 78. Cool? Okay, so all the denominators look the same, don't they? So now it's time to get rid of the common denominator. So we've done this quite a number of times at this point. Multiply everything by that common denominator. Cancel out the denominators. And we are left with a nice simple equation of 3t plus 2t equals 78. Left side, adding like terms. Dividing by that 5 to get the t by itself. And this is in hours, isn't it? Because we've been talking hours this whole time, right? Now, watch the directions. Because sometimes the directions may say give them an exact answer, give them a fraction, which means you would leave it this way. But sometimes they say, hey, give me this answer 1 decimal place. And when you do, 78 divided by 5 is approximately 15.6 hours. Cool? All right. So it does take less time working together, right? In this case, the beginner took 39 hours. The experienced guy took 26 hours. And when they worked together, it took them only 15.6 hours, just under 16. As always, we should check our work, plug it back in, and we end up with a true statement. Cool? Love it. Okay, so and there's the statement. Let's look at the last type of problem. We're looking at a distance problem. And right here should be a multiplication symbol. Distance is equal to rate times time. That's our formula. How far you travel, what's the speed you travel, and how long is it going to take you? So let's take a look at the lazy river. The speed of the lazy river's current is 5 miles an hour. A boat travels downstream in the same time it travels 10 miles upstream. They want to find the speed of that boat in still water when there's no movement in the water. Now here's the deal. The fact that they're talking about miles, the fact that they're talking about miles per hour, the fact that they're talking about time tells me that this is a distance problem. Now, I'm going to sidetrack you a second. So, remember being a kid on your bike, and you are traveling at 5 miles per hour, okay? And you had the wind at your back, and the wind was traveling at 2 miles per hour. Are you still going at 5 miles an hour? No, because since the wind is helping you, you were able to go even faster, which means you had a total of 7 miles per hour you were actually traveling, right? Okay, so how did we get that? Yeah, your speed of 5 plus the wind of the speed of 2 gave you that 7. Does that make sense? But what happens if you're traveling at that 5 miles per hour? So let me redo it over here. What happens if you're traveling at that 5 miles per hour in this direction, and now you got a headwind? And that headwind is at 2 miles per hour. You got to pedal faster, don't you? Are you still traveling at 5 miles per hour? Yeah, no, because that wind is slowing you down, isn't it? It's not going faster than you, which means it's not blowing you all over the road, but it's slowing you down, isn't it? So here's your speed, and here's the speed of the wind. Now what do? Do I still add? Yeah, you're right. No, I subtract. Yeah, I take my speed, because my speed is bigger than the speed of the wind, which means I would only be traveling at 3 miles per hour, wouldn't I? Okay, So let's look at this lazy river. We got a boat traveling. So read and reread the problem. It's a distance problem because we said miles per hour, miles, and time. And we can rewrite the formula any way we want it. Okay, so if I want to get time by itself, I would simply divide both sides by r, right? That's how they get this formula. Okay, now, if the boat is going downstream, is the water going with it or against it? Yeah, with it, which is why it's an addition sign. The rate of that boat and the rate of the water added together. Okay? In this case, our rate is the speed. If the boat is going upstream, is the water going with it or against it? Yeah, the water's going against it, which is why the boat speed minus the speed of the water. Okay? Okay, so take a look. We knew that going downstream was 10 miles, or 20 miles, excuse me, and going upstream was 10 miles. So the distance downstream was 20 miles, and the distance upstream was 10 miles, okay? The rate in still water, do I know how fast the boat traveled in still water? Nope, so we're just going to call it R. But what I do know is the speed of the current is 5. So, remember, R is the speed of the boat in still water. 5 is the speed of the current. Downstream, we said, was an addition problem. The boat speed plus the 5 of the water. The rate for the upstream is subtraction. With boat speed minus the speed of the water, because now he's going to go slower. The time is the same, is what they said in the problem. So both of these are equal to time, aren't they? And remember what we said in the last slide. I can take my distance problem, d equals r times t. I can take that distance problem formula and I can rearrange it, which I could have the time just being rewritten as distance over rate, which is exactly what they did here. The distance divided by the rate. The distance divided by the rate. Okay, and since the time is the same, that's going to make our lives a whole lot easier. Distance over rate. Distance divided by rate. This is on the upstream side. This is on the downstream side. Distance over rate. Okay. Now, this part is the easy part, right? We have to make the denominators the same, which means we get to multiply top and bottom by r minus, oops, sorry about that, which means I multiply this denominator by r minus 5, as well as this numerator. And on fraction 2, I multiply by r plus 5 to make them look the same. And now that the denominators are the same, I can do some canceling, right? Which will leave me with this line and I just multiply it through, and in this case I get the speed of the boat in still water. No movement whatsoever. Cool? Okay, let's take a gander. Always check your work, plug it back in, and when I plug it back in, I end up with a true statement because both sides are equal to 1. Got it? Okay, so you have fun with this. Go back over the slides, pause them, go slow, okay, and I'll see you on the flip side. Bye!